Welcome to this comprehensive scientific lecture on bubbles and foams. Today we're going to explore the fascinating physics, chemistry, mechanics, optics, and thermodynamics of these ubiquitous structures that appear everywhere from your morning coffee to advanced materials engineering. Let's start with the fundamentals. What exactly is a bubble, and what is a foam? A bubble is a thin liquid film that encloses a volume of gas. Think of a soap bubble floating in the air. It's essentially a spherical shell of soapy water surrounding air. A foam is a collection of many gas bubbles separated by thin liquid films. Examples include shaving cream, the head on your beer, or the foam in a fire extinguisher. Here you can see the difference. A single bubble on the left is an isolated structure, while a foam on the right consists of multiple bubbles packed together. Now let's dive into the physical properties. The most important property governing bubble behavior is surface tension. Surface tension is defined as the energy required to increase the surface area of a liquid by 1 unit. It's measured in joules per square meter, or equivalently, newtons per meter. Gamma equals energy divided by area, which is equivalent to force divided by length. For water, gamma is approximately 72 millinewtons per meter at room temperature. But why does surface tension exist in the first place? It's due to the cohesive forces between liquid molecules. Molecules in the bulk of the liquid are attracted equally in all directions by neighboring molecules. But molecules at the surface have no neighbors above them, only below and to the sides. This creates a net inward force, causing the surface to contract and minimize its area. One of the most important equations in bubble physics is the Young-Laplace equation. This relates the pressure difference across a curved interface to the surface tension. Delta P equals gamma times the sum of 1 over R1 plus 1 over R2, where R1 and R2 are the principal radii of curvature. For a spherical bubble, both radii are equal to the bubble radius R. This simplifies to delta P equals 2 gamma over R. This tells us that smaller bubbles have higher internal pressure. Now here's an important detail. A soap bubble actually has two surfaces, an inner surface and an outer surface, so we need to account for both. For a soap bubble, delta P equals 4 gamma over R. The factor of 4 comes from the two surfaces. Let's do a back-of-envelope calculation. What's the pressure inside a soap bubble with a radius of 1 centimeter? The radius is 0.01 meters. For soapy water, gamma is approximately 0.025 newtons per meter. This is lower than pure water because soap produces surface tension. Delta P equals 4 times 0.025 divided by 0.01, which gives us 10 pascals. 10 pascals is approximately 0.01% of atmospheric pressure. This seems small, but it's significant enough to keep the bubble inflated. Now, what if we had a much smaller bubble? Let's say 1 millimeter in radius. Now delta P equals 100 pascals. Notice that when we decrease the radius by a factor of 10, the pressure increased by a factor of 10. This inverse relationship is fundamental to understanding bubble coalescence. Now let's discuss the chemistry. Pure water cannot form stable bubbles. You need surfactants, also known as surface active agents. Surfactants are amphiphilic molecules, meaning they have both hydrophilic water-loving and hydrophobic water-repelling parts. A surfactant molecule has a hydrophilic head that loves water and a hydrophobic tail that avoids water. At an air-water interface, the molecules orient themselves with heads in the water and tails pointing toward the air. Common surfactants include soap, detergents, proteins, and lipids. Even your saliva contains surfactants, which is why you can blow spit bubbles. Surfactants reduce surface tension dramatically. Pure water has a surface tension of 72 millinewtons per meter, but soapy water can be as low as 25 millinewtons per meter. Surfactants also enable something called the Marangoni effect, which is crucial for bubble stability. The Marangoni effect is a flow induced by gradients in surface tension. When a thin film is stretched, surfactants become less concentrated in that region, increasing local surface tension. When a region of the film is stretched and becomes thinner, the higher surface tension there pulls liquid back from surrounding areas. This self-healing mechanism helps stabilize the film against rupture. Now let's explore the mechanical properties. Soap films and foams exhibit remarkable elastic behavior. Surface elasticity, also called the Gibbs elasticity, describes how the surface tension changes when you stretch the interface. E equals d gamma divided by d natural log A, where A is the area. This tells us how much the surface tension changes per fractional change in area. This elasticity is why foams can support their own weight and maintain structure. Think of shaving cream. It doesn't immediately collapse under gravity. The structure of foams is governed by Plateau's laws, discovered by Belgian physicist Joseph Plateau in the 1860s. Law 1. Soap films meet in groups of 3 along edges called plateau borders, and these films meet at 120-degree angles. Law 2. These edges meet in groups of 4 at vertices, with angles of approximately 109.47 degrees. This is the tetrahedral angle. Here you see 3 films meeting at 120 degrees. This configuration minimizes the total surface energy. Why 120 degrees? Because this angle minimizes the total surface area, and therefore the surface energy, for a given volume of gas. Let's move on to the beautiful optical properties of bubbles. The rainbow colors you see on soap bubbles are due to thin film interference. When light hits a soap film, some reflects from the top surface and some penetrates and reflects from the bottom surface. These 2 reflected waves can interfere constructively or destructively. Light ray 1 reflects from the top surface. Ray 2 travels through the film, reflects from the bottom, and exits. The path difference determines whether they interfere constructively or destructively. For constructive interference, the condition is that the path difference equals an integer multiple of the wavelength. 2nt equals m lambda, where n is the refractive index, t is the film thickness, m is an integer, and lambda is the wavelength. Different colors, which have different wavelengths, will interfere constructively at different film thicknesses. This is why you see swirling rainbow patterns on bubbles. As a soap bubble ages and drains, it becomes thinner. The colors shift from blue to green to yellow to red. Just before bursting, very thin regions appear black because the film is too thin for visible light interference. Let's calculate the film thickness needed for constructive interference of green light. Green light has a wavelength of about 550 nanometers. The refractive index of water is approximately 1.33. For the first order, m equals 1, we get t equals 550 divided by 2 times 1.33, which is approximately 207 nanometers. That's incredibly thin, about 1/500th the thickness of a human hair. Now let's examine the thermodynamics of bubbles and foams. These systems are fascinating from an energy perspective. A fundamental principle is that bubbles minimize their surface area for a given volume. This is why isolated bubbles are always spherical. The sphere has the minimum surface area for any given volume. The surface area of a sphere is 4 pi r squared, and the volume is 4/3 pi r cubed. The surface free energy is the energy cost of maintaining the interface. G surface equals gamma A equals 4 pi r squared gamma. For a soap bubble with 2 surfaces, multiply by 2. Foams are thermodynamically unstable. They want to minimize total surface area, which drives several aging processes. There are 3 main mechanisms by which foams age and eventually collapse. First is drainage. Gravity pulls liquid downward through the plateau borders. This causes films to become thinner at the top of the foam. Second is coarsening, also called Ostwald ripening. Remember that small bubbles have higher internal pressure. Gas diffuses through the liquid from high-pressure small bubbles to low-pressure large bubbles. P small is greater than P large, causing gas to flow from small to large bubbles. Over time, small bubbles shrink and disappear while large bubbles grow. Third is coalescence. When films become too thin, they rupture. Adjacent bubbles merge into larger ones, reducing the total number of bubbles and total surface area. Here's a schematic of coarsening. The smaller bubbles on the left gradually lose gas to the larger bubble on the right. Eventually, the small bubbles vanish. We can estimate the coarsening rate using a simple diffusion model. The rate at which gas diffuses is proportional to the pressure difference and the diffusion coefficient. J is proportional to d times delta P divided by d, where d is the diffusion coefficient and d is the liquid film thickness. Delta P equals 4 gamma over r small minus 4 gamma over r large. For typical foams, the coarsening timescale ranges from minutes to hours, depending on the liquid's diffusion coefficient and viscosity. Let's do an energy analysis. What happens when two identical bubbles coalesce? Initially, we have two bubbles, each with radius r. The total surface area before is 2 times 4 pi r squared, which equals 8 pi r squared. After coalescence, we have one bubble. Conservation of volume gives us the new radius. The total volume is 2 times 4/3 pi r cubed equals 4/3 pi r cubed. Solving for r, we get r equals 2 to the 1/3 power times r, which is approximately 1.26 times r. The surface area after is 4 pi r squared, which equals about 6.35 pi r squared. Notice the surface area decreased from 8 pi r squared to 6.35 pi r squared. This means energy was released during coalescence. The process is thermodynamically favorable. Delta E equals gamma times the area change, which is negative 1.65 pi r squared gamma. The negative sign indicates energy release. Viscosity plays a crucial role in foam stability. Higher viscosity slows down all the aging mechanisms. The drainage time is proportional to the liquid viscosity. Thicker, more viscous liquids drain more slowly. The drainage time is proportional to eta rho gh divided by gamma, where eta is viscosity, rho is density, g is gravity, h is foam height, and gamma is surface tension. This explains why shaving cream, which has high viscosity, can last for minutes, while beer foam, with lower viscosity, collapses in seconds. Now let's explore the many practical applications of bubbles and foams across different fields. First, the food industry. Foams are everywhere in food. Examples include whipped cream, meringue, bread, ice cream, and beer foam. In bread, yeast produces carbon dioxide bubbles that make the dough rise and create the spongy texture. Second, material science. Foamed materials like polyurethane foam and metal foams have unique properties. These materials combine low density with high strength-to-weight ratios and excellent thermal insulation. They're used in everything from packaging to aerospace applications. Third, firefighting. Foam fire suppressants work by forming a blanket that excludes oxygen and cools the fuel. The foam creates a physical barrier between the fuel and oxygen in the air. It's particularly effective for liquid fuel fires like gasoline or oil fires. Fourth, cleaning and personal care products. Soaps, shampoos, and detergents all produce foam. The foam helps distribute cleaning agents over surfaces and traps dirt particles within the bubble structure for easy removal. Fifth, medical applications. Ultrasound contrast agents are actually microbubbles. These microbubbles, typically 1 to 10 micrometers in diameter, strongly scatter ultrasound waves. Injected into the bloodstream, they enhance the visibility of blood vessels and organs during imaging. Sixth, environmental applications. Foam fractionation is used to remove pollutants from water. Surfactants attach to pollutant molecules. When air is bubbled through contaminated water, the pollutants concentrate in the foam, which can then be removed. Seventh, mining and mineral processing. Froth flotation separates valuable minerals from ore. Selective surfactants make desired mineral particles hydrophobic. These particles attach to rising bubbles and float to the surface, while unwanted material sinks. Let me introduce an advanced topic, the Kelvin problem. Lord Kelvin asked, what is the most efficient way to partition three-dimensional space into equal volumes? For over 100 years, the best-known answer was Kelvin's tetrachedecahedron, a 14-faced polyhedron. Each cell has 14 faces, 6 squares, and 8 hexagons. But in 1993, physicists Denis Wier and Robert Phelan discovered a structure with 0.3% less surface area than Kelvin's. This structure was famously used in the design of the Beijing National Aquatic Center for the 2008 Olympics. Let me pose a question for you. Why do small bubbles tend to disappear in a foam while large bubbles persist? Take a moment to think about it. The answer relates to the Young-Laplace equation. Small bubbles have higher internal pressure because pressure is inversely proportional to radius. This pressure difference drives gas to diffuse from small bubbles through the liquid to larger bubbles with lower pressure. Here's another question. Why are soap bubbles always spherical when floating freely? The sphere is the shape that minimizes surface area for a given volume. Since surface tension creates an energy cost proportional to area, the bubble naturally adopts the spherical shape to minimize its free energy. Let's discuss an interesting instability, the Rayleigh plateau instability. This explains why a water stream breaks into droplets. A cylindrical column of liquid is unstable. Small perturbations grow over time, eventually causing the cylinder to break into spherical droplets. The critical wavelength for instability is lambda critical greater than 2 pi r cylinder. Perturbations with wavelengths longer than the circumference will grow. Here you see the progression. A uniform cylinder develops bulges and necks. The necks thin and eventually pinch off, forming separate spherical droplets. This happens because the droplet configuration has lower total surface area than the cylinder. Foams exhibit fascinating rheological properties. They behave as non-Newtonian fluids. At low stresses, foams behave like elastic solids. They deform, but return to their original shape. At high stresses, they flow like viscous liquids. Foams have a yield stress, a minimum stress required before they begin to flow. Below this threshold, they act solid. Above it, they flow. When the applied stress tau exceeds the yield stress tau y, flow occurs. This is why shaving cream stays on your face until you spread it with your hand. Let's estimate how long a soap bubble can last before popping. A bubble pops when the liquid film becomes so thin that it's unstable to thermal fluctuations or dust particles. The critical thickness is typically around 50 to 100 nanometers. T-critical is approximately 50 to 100 nanometers. A freshly formed soap bubble might have a film thickness of 1,000 nanometers. T-initial is approximately 1,000 nanometers. The drainage rate depends on viscosity and gravity. For water with low viscosity, drainage is fast. The drainage velocity is approximately rho(gh) squared divided by 3 eta, where h is the film thickness. Combining these factors, a typical soap bubble in still air lasts anywhere from 30 seconds to a few minutes before the film becomes critically thin and ruptures. Foams have interesting acoustic properties. They're excellent sound absorbers. When sound waves propagate through foam, they cause the gas in the bubbles to compress and expand. This viscous dissipation and thermal conduction between gas and liquid absorb acoustic energy. This property is exploited in soundproofing materials, acoustic panels in recording studios, and anechoic chambers used for acoustic testing. Soap films naturally form minimal surfaces, surfaces with zero mean curvature that minimize area. Mathematicians and architects have used soap films to visualize and study minimal surfaces. When you dip a wireframe into soap solution, the film that forms is a minimal surface spanning that boundary. A famous example is the catenoid, the surface formed between two parallel circular rings. This surface has constant negative curvature and appears in architecture and structural engineering. Sometimes we want to prevent or destroy foam. That's where anti-foaming agents come in. Anti-foaming agents, also called defoamers, are substances that destabilize foam by disrupting the surfactant film. Common antifoams include silicone oils, mineral oils, and alcohols. They work by spreading rapidly over the film surface, displacing the stabilizing surfactants and causing film rupture. Anti-foaming agents are crucial in many industrial processes, like fermentation, paper manufacturing, and wastewater treatment. They're also used in washing machines to prevent excessive foam and in cooking oils to prevent foaming at high temperatures. Let's do one more calculation. How effective is foam insulation compared to solid materials? The thermal conductivity of air is about 0.026 watts per meter Kelvin. Solid polyurethane has thermal conductivity of about 0.18 watts per meter Kelvin. But polyurethane foam, which is 95% air by volume, has thermal conductivity close to that of air, around 0.026 watts per meter Kelvin. That's nearly 7 times better insulation than solid polyurethane. This demonstrates that the trapped air is doing most of the insulating work. The solid polymer just provides structure to prevent air circulation. Let me briefly mention a highly speculative but fascinating concept: quantum foam. At the Planck scale, about 10 to the minus 35 meters, some theories suggest that spacetime itself may have a foamy structure due to quantum fluctuations. The Planck length equals the square root of h bar g divided by c cubed, approximately 1.6 times 10 to the minus 35 meters. This is highly theoretical and remains unproven, but it's a remarkable example of how foam-like structures might appear at vastly different scales, from soap bubbles to the fabric of spacetime itself. Let me summarize the key concepts we've covered in this comprehensive lecture. Surface tension is the fundamental driving force behind bubble and foam behavior. It arises from molecular cohesion and creates an energy cost for interface area. The Young-Laplace equation tells us that pressure is inversely proportional to radius. This drives gas diffusion from small to large bubbles. Surfactants stabilize foams by reducing surface tension and enabling the Marangoni effect, which provides self-healing behavior. Thin film interference of light produces the beautiful rainbow colors we see on soap bubbles. Foams are thermodynamically unstable and age through drainage, coarsening, and coalescence, all driven by the tendency to minimize surface energy. Applications of bubbles and foams span an enormous range, from food science to advanced materials, from firefighting to medical imaging. Plateau's laws describe the optimal geometry of foam structures, with films meeting at 120 degrees and edges at tetrahedral angles. Foams exhibit complex non-Newtonian rheology, acting as elastic solids at low stress and viscous liquids at high stress. Bubbles and foams represent a beautiful intersection of physics, chemistry, mathematics, and engineering. These seemingly simple structures embody deep principles of thermodynamics, surface science, optics, and mechanics. From children blowing soap bubbles to advanced architectural materials and medical technologies, the science of bubbles and foams touches our lives in countless ways. Despite over a century of research, foam science remains an active field. Questions about foam stability, the statistical mechanics of coarsening, and optimal foam structures continue to challenge researchers. Thank you for joining me on this comprehensive journey through the science of bubbles and foams. I hope you've gained a deeper appreciation for these fascinating structures that are all around us.